sometimes point matching isn't quite good enough for what you need. If you want to operate very closely around a very small range, then you can use derivative matching, which would match a higher order function, but only at one specific point. So it can be more accurate, but only in a very small range. So to get the equations for derivative matching, we take Freudenstein's equation and then take its derivative. So first derivative, basically we're taking the derivative of theta 4 with respect to theta 2, which is the same as d gamma d beta. So write that here. So we match not just the first derivative, but we'll also need the other derivatives, second derivative and third. So the first derivative here is not too bad, but you go to second derivative, gets a little bit scarier. Third derivative is just kind of a monstrosity. Now, because there's so much math here, rather than work it out on the whiteboard, I'm just going to go through the PowerPoint. But you'll get to see all of the different things that we calculate, and then I'll show y'all how to start it off for a problem with actual numbers. So then we can put the first three derivatives into the following form, this form at the bottom here. So we've got coefficients A, B, C, D, and E, where the I represents which derivative it is. So for first derivative, second derivative, and third derivative, you can put these letters into a table and calculate them. So you've got the chart, then whatever function it is that you have chosen for your derivative matching, then you would calculate all of these little subderivatives and fill this table out. So that's something that you would need to do by hand. After this point, it's possible to calculate things in MATLAB, but finding all of these specific derivatives is something that you would need to do by hand. So then you can simplify the equations even more by putting in these other coefficients. So for first, second, and third derivative, you'll get one of these equations. So then that will be 9, D, E, and F for 1, 2, and 3. So if we look at Freudenstein's equation plus the three derivative equations, then we have 4 equations and 4 unknowns. So 3 of the unknowns are the K coefficients, K1, K2, K3, and then the operating point, theta 2 desired. So this is different than point matching as far as choosing the operating point, because for point matching, we chose the input and then a function that related input and output. Here, we'll choose the design value for the output because we want to operate super specifically around that output point. And then we'd have to back calculate what the input should be for it. So regroup the equations, get all of these giant mess of things, and then I have to give a little shout out to my predecessor, Brian Slaybach, who actually typed all of these slides and loves kinematics math a lot more than I do. I like the application, so we'll get to that in a bit. So that previous equation, we could solve it for tangent of theta 2 desired. So every value of the tangent will give 2 solutions for theta 2 desired. So then there's 4 possible values. Now this is because if you have a tangent, then it's composed of a sine and a cosine. So depending on whether sine or cosine is positive or negative, you can get those 4 possible values for theta 2 desired, one for each quadrant. So you pick just one of them. Now, if an imaginary solution comes out, then rethink your life. You got to choose a new position. If 2 values of them are different by pi, then they'll make the same linkage. So it doesn't matter which one you pick. But the main thing is imaginary solution, not possible, cannot physically construct a linkage to match that. So if you get that, go back to the drawing board. So overview. First, figure out the function you're trying to approximate. Then choose a design position for beta and theta 4 desired. So you pick those, whatever they are. And then find the derivatives of the function. Remember that when you take the derivative of the function, d theta 4 is the same as d gamma. D theta 2 is the same as d beta. So it doesn't matter which way you calculate. Then you get the lowercase coefficients, the uppercase coefficients, and the lambdas at the particular design position for I equals 1 to 3, meaning first, second, and third derivatives at this one particular point. So then finally, solve out that quadratic equation with tangents and lambdas to figure out what theta 2 desired is. There's 4 possible outcomes, so you pick one of them. So then there are some G coefficients that you can calculate, and this is why MATLAB is helpful. You just type all this stuff in. And then finally, from those G coefficients, then you can get K1, K2, K3, and then finally get the R values from K1, K2, and K3. So again, pick the ground length, and then you'll be able to calculate the other 3. If for some reason this comes out with negative values for R, start back at the beginning. Repick a function, repick a point, and figure out a better linkage. So this is a lot of math. Now I'm going to show y'all kind of how to start this off basically for a problem with real actual numbers. And then we'll look at the MATLAB code and you'll see how I've just typed these things in there so I didn't have to calculate them all by hand. So here's a water pouring example. We're going to figure out a function and get its derivatives with some actual numbers. So just to kind of explain this, so we have the 4-bar linkage with the standard R vectors. Theta 4 is the output angle, theta 2 is the input angle. Change in output is gamma, change in input is beta. So that's how those derivatives work out. Now, we need a function that relates beta and gamma. So this is not going to be a linear function because for derivative matching, we use something higher order. Derivative of a line would just be a constant. So then, there would be no point, there would be no third derivatives. So we need to pick something that is higher power. So let's say the one I use for this one is gamma equals 1.2 beta minus 0.1 beta squared minus 1 beta cubed. So that was my function that relates gamma and beta. So now we need to figure out the first 3 derivatives. So we need d gamma, d beta. So that'll be 1.2 minus 0.2 beta minus 3 beta squared. Then second derivative, d squared gamma d beta equals negative 0.2 minus 6 beta. And then d cubed gamma d beta cubed equals negative 6. So y'all remember that table we had to fill out? Well, since d theta 4 equals d gamma and d theta 2 equals d beta, then we can say that the first derivative is d theta 4 d theta 2. Second derivative is d squared theta 4 d theta 2 squared. And then the third derivative is d cubed theta 4 d theta 2 cubed. So now that we have all those, we can put them in this table with the lowercase coefficients and calculate all of that stuff. So I'm going to show you all my MATLAB code, but first, let's just specify one more thing, the operating point. So operating point, I use theta 4 equals 155 degrees, which corresponded to beta equals 50 degrees, or theta 2 equals 110 degrees. So this was the operating point that I took the derivatives at. So using all these numbers, put them into MATLAB. So let's take a look at that. So you can see here, I chose my ground link and I chose the coefficients. So these coefficients just match to the equation I used on line 6. So that's the same thing that I wrote down on the whiteboard. And then with the derivative method, so plugged in all 3 of the derivatives here and calculated the lowercase coefficients from that. Turns out you don't need E. So then I just plugged in equations for the uppercase coefficients, the lambdas, and note that all of these are matrices because we have first, second, and third derivatives. So then figured out that operating point, then the G coefficients, then the Freudenstein coefficients, and then finally solve for the link lengths. So you can see here on the graph that we're matched at one point and the slope at that point. Now, don't be deceived by the monstrous scale on the y-axis. So it's actually not a straight line. Let's zoom in to look there. So if we zoom in a little closer, and then let's try to get for theta 4 being basically plus and minus about 360. That will give us a good picture. So you can see that we're matched at the point and its slope for only a very small range. Looks like maybe like theta 2 being about, well, it's hard to see there. I guess about -25, maybe to +10 or something. That's the only range that the function is actually valid for. But around that area, we do operate very well. So you can see here the Freudenstein coefficients, K1, K2, K3, and the R values R1, R2, R3, and R4.